Welcome to the first session of the reading group on the assumptions of physics. We are still waiting that people are coming in. If you are seeing this live, I would encourage you to write in, introduce yourself in the chat so that we have a sense of who is here and what their background is. If you guys don't mind, the guys that are online already I'd like to go around if people can give a brief introduction, just so that I know what level, what is your interest and so on. So Rudra, why don't you start?
Hey guys, so I did my bachelor's in mathematics from Cornell University and literally just submitted the master's dissertation like 2 days ago from King's College London in theoretical physics,
On what?
superstring theory.
Oh, super
Just the
string.
literature review because my advisor didn't want me to get too creative with because I think I remember if people remember I gave a talk here and one of the I think Dr. Karkasi brought up Kähler manifolds, so I was trying to sort of work with compactified Kähler manifolds in my compactification in superstring theory. I was planning on using some version of my theorem for the entire Kähler geometry. I just didn't have enough time, it seems.
Okay. Right. So Artem, why don't you go next?
Yeah, so hello everyone. Right now I'm not a student. I've just finished my bachelor's degree here in Ukraine, in Lviv. My bachelor's was in quantum computing, but like generally I'm just curious and excited about physics as a way to get closer to understanding how our universe works. So my plans further are to maybe fill my gaps in math and physics, especially like classical mechanics. And then I'm gonna go study more QFT, GR, and stuff like that. Really interested in that.
Okay. Ruli? Oh, and if I might badly mispronounce your names, please do tell me.
It's pronounced Rowley, but I don't particularly
Raleigh.
care.
Okay.
My name's Rowley. I'm Rowley Freeman since my last name isn't on here. I'm a just finished bachelor's degree at Oxford for Maths and Computer Science. Let me see. And I'm mostly doing this because I took the quantum theory course and got really annoyed at how the momentum operator is not an operator. So want to figure out how these things actually work there.
Okay, Alina?
Right. Hi, everyone. I'm Alina. I did my master's recently on applied physics. Still, well, not completed yet. Still waiting to present my final dissertation. And now I'm doing a master's on philosophy, mainly interested in philosophy of physics, foundations of quantum mechanics. And I kind of came to this space through the summer course, the last summer course. Summer course or summer school, I suppose summer school. And I was very taken aback by just how much I didn't understand classical mechanics. Like I was so focused on quantum mechanics, but even classical mechanics I didn't understand that well. And so that's why I'm here, really interested in this project.
Yeah, it's one of the things that I realized when I was trying to understand quantum mechanics as well, that I really didn't understand classical mechanics either. And then once I understand classical mechanics, it's easier to understand quantum mechanics as well. Let's move to Robbie.
Hello, my name is Robbie. I'm not sure of my camera. I don't even have an option to turn my camera on right now. But yeah, I did a bachelor's in math and physics a few years ago, and I'm currently applying to PhD and master's programs. I'm really interested in quantum foundations, and generally, I think physics is just kind of a mess. So I really like Gabrielle's research program. Yeah.
Okay, Tobias.
Hi, I'm Tobias. I'm from Germany. I found Gabriele probably while I was doing my master's, and I was just super interested, but like I guess scared to contact him. So it took me like a year or so, and then I was like, yeah, this is actually what I want to do for a PhD. That would be super cool. So I just asked him, and I just did it, and now I'm here. It's kind of crazy. So I'm just starting my second year in the grad program here at the University of Michigan. I'm working with Gabriele. Yeah, and I am also, of course, super interested in quantum mechanics, figuring it out. I remembered while I was applying that actually, even when I was like 16 in like high school, I wrote a research article like about the Heisenberg uncertainty relation and its consequences for determinism. So like when I was 16, I already knew I really want to know what the hell is going on. I had no idea that I will do research on this. I couldn't imagine. Yeah, so this is pretty cool.
Okay, so I think we went through everybody, and I see that there are some people viewing from YouTube. Again, if you want to put in the chat, introduce yourself, that would be nice. I I was thinking that we would just go through the book and read sort of in turn in an order of operation which needs to be developed, and I'm going to be distracted by the cat, as Tobias also. Okay, so we have two choices. Either we use the latest version of the book, which is the 2.0 that you can get from the website, and this is the link. Otherwise, we could go to the latest sort of development version, which doesn't really have that many changes at this point. I will keep open up the one the development version, because typically what like the only time that we really did a reading group like this was before the first release of the book, and so while people were talking and finding out typos, mistakes, or I would go and fix the text. So this is what I'm gonna do right now. If we find the things that are unclear or just spelling mistakes, with the idea that then I will, at the end of the session, I will push in the new version on GitHub, so people can find the new version. I also have ready my tablet in case that we need extra discussion on some other things. If so, one of the things that would be useful for me is if we can find places or ideas for sort of graphical representation, diagrams, and whatnot that would make the exposition easier. The book right now, it's not really meant to be so didactic, in the sense that it just tries to cram all of the things that we found, at least in some place, so that they're written down. And so if there are parts of that you guys don't have the background, or we need to do a detour, I'm perfectly happy to do it. And if it's something where we need to drill down in another session and it's only interesting to some people because it's just one or two people that are missing some background and everybody else has it, I'm also happy to organize these extra sessions. So the way that I would do it, I would just open the book, go to the part of reverse physics, and then starts reading one paragraph at a time going around. Does that sound good to everybody? Okay, so we need to get an order operation. So I would suggest, Tobias, why don't you start, and then you call somebody else, and that somebody else has to remember that when Tobias has finished a paragraph, he will need to start next, and then we go on until we go back to Tobias.
Okay, and we open like the book ourselves, like everybody has their own
I
book open.
think so. I don't know. Like, do you guys want me to share the
I mean,
text?
I will probably want to read my own version anyway.
That's
Uh,
kind of what I thought, because people might want to skip ahead and so on while it's being read, or look
yeah,
at the figures and so on.
yeah, okay. I
And
will
and
just
for people
try.
following online, there is the link, and people can go and get it, even if you're watching the recording. you can decide
Yeah.
whether also to read at faster speed because
Yeah. Okay. Yeah, then I can just start. So we start with reverse physics,
yeah.
part one, and then okay, I'm just gonna start then. So reverse physics is an approach to the foundations of physics that analyzes known theories to identify those physical principles and assumptions that can be taken as their conceptual foundation. This is the analog of reverse mathematics, program and mathematical logic that seeks to determine which axioms are required to prove mathematical theorems. So while some physical theories such as Newtonian mechanics, thermodynamics, and special relativity are
That in
indeed
principle
founded,
was already a paragraph, so
sorry. Yeah, is it worth getting like a comment on that? Maybe people don't know what reverse mathematics is, but
so if you guys, at the end of every paragraph, anybody is welcome to stop, ask questions, and so on. So Tobias, you have to choose your next, the person that goes next after you.
I wonder if I could change, make a small window where I can see all the people. Okay, next to me on my panel, I see Artem. Would you like to
Okay,
continue?
so yeah, well, some physical theories such as Newtonian mechanics, thermodynamics, and special relativity are indeed founded on laws or principles. Many theories such as Hamiltonian and Lagrangian mechanics, quantum mechanics, and general relativity are based on mathematical relationships that are simply postulated without a strict physical justification. Most modern theories are of the latter type, as theoretical physicists have increasingly focused on mathematical ideas rather than physical starting points. Therefore, we do not know why the state of a quantum system can be represented by a ray in a Hilbert space, or what exact relationship is represented by the Einstein field equations. The goal of reverse physics, then, is to find suitable physical premises that can function as a more proper foundation for each theory. We stress that the premises have to be of a physical nature, such as the system under study is isolated or the quantity is additive under system composition. That is, they must be principles or assumptions that express some physical idea, not some abstract mathematical notion. And let's go to Rowley. Is that right? Did I remember correctly?
Yeah. So bit of a weird thing is that it looks like the list of people displays differently on everyone's screen, so it's going to be kind of disorganized.
Correct.
Just hope to
So that's why
remember.
everybody has to remember who is the person that is before them, so that they can start.
Yeah, but it's going to be still kind of randomized anyways. Maybe we could make a list of
I already
every
started the
people
list.
in
I'm
order.
gonna put it in the chat once we
Yeah.
are through everybody once.
Anyways. Another issue in modern physics is that it is currently a patchwork of different theories, and one is trained to match patterns and examples to decide which problems or what aspects of a larger problem should be treated with a particular theory. The goal here is to fully understand what physical situation each mathematical structure can suitably describe, what connections can be made across different theories, and what exactly are the true limits of applicability of the different physical theories. One of the main results of reverse physics is that there are some core ideas that are shared by all physical theories, and that, in fact, physical theories are not as disconnected from each other as generally thought. And I'll have Robert Yotzi go next.
Yeah, thank you. I just had a thought. If people are watching on YouTube, they don't see anything that we're reading, so maybe it would be worthwhile to screen share or something.
I can screen share.
But just a thought going forward. Okay. While this work explores connections between different mathematical and physical disciplines, it would be impractical to provide even a concise introduction to all. Therefore, when encountering concepts like information entropy, Minkowski spacetime, function spaces, quantum observables, Lagrange multipliers, intensive quantities, and so on, we can only provide the definition with very limited context. as most of the space must be dedicated to the connections between those concepts. It is up to the reader to decide whether to invest additional time on other sources or to simply make a mental note and proceed further. Rudra?
By nature, reverse physics does not aim to be mathematically precise, but rather conceptually precise. While the goal is to create a dictionary between physical concepts and their mathematical representation, this mapping cannot be absolutely perfect for a simple reason. We have no guarantee that the current mathematical structures are the correct ones to capture the physical ideas. Conversely, we cannot give a precise mathematical characterization of the physical ideas if these are not conceptually clear. Therefore, conceptual clarity has to come before formal precision. Yet, it is true that to reach full conceptual clarity, the ideas have to be sufficiently refined to allow a formal definition. This task is the purview of physical mathematics, which aims to find physically meaningful mathematical structures, starting from definitions and axioms that can be fully supported by physical requirements and assumptions. Yet it would be premature to engage in such activity without having thoroughly tested the conceptual framework beforehand. Okay.
Okay.
I
Any
think
comment on question on the preamble? Okay, that's basically yeah. So we're playing around with concepts to understand what the concepts are, and then only once we have the right concepts, we can actually go and make sure that all the T's are crossed and the I are dotted. So that's it. So we can start to the classical mechanics part.
Is it Tobias again?
No, I think Alina hasn't gone yet, right?
yeah, it's
Yes.
Alina.
Haven't gone yet, no. So I go now?
Yeah, go
Yes?
ahead, Alina.
Okay. Chapter 1, Classical Mechanics. The standard view in physics is that classical mechanics is perfectly understood. It has three different but equivalent formulations, the oldest of which, Newtonian mechanics, is based on three laws. Classical mechanics is the theory of point particles that follows those laws. Unfortunately, this view is incorrect. It's very short. Should I keep going or should we just go back to Tobias
No,
now?
we can continue on the. It's just that are we cycling back?
Yeah, I think
so.
now it's Tobias now, yeah.
Tobias, go.
Yes.
Tobias, sorry.
I just put the order in the chat. Okay. Now I gotta organize my windows, sorry. So we will see that the three formulations are not equivalent in the sense that there are physical systems that are Newtonian but not Hamiltonian and vice versa. There are also a number of questions that have been left unanswered, such as the precise nature of the Hamiltonian or the Lagrangian, and what exactly the principle of stationary action represents physically. While shedding light on these issues, we will also find that classical mechanics already contains elements that are typically associated with other theories, such as quantum mechanics, field theories, uncertainty principle, antiparticles, thermodynamics, statistical mechanics, thermodynamic and information entropy conservation, or special relativity, energy as the time component of a four vector. In other words, the common understanding of classical mechanics is quite shallow, and its foundation are, in fact, not separate from the ones of classical statistical mechanics or special relativity.
What reverse physics shows is that the central assumption underneath classical mechanics is that of infinitesimal reducibility, IR. A classical system can be thought of as made of parts, which in turn are made of parts and so on. Studying the whole system is equivalent to studying all its infinitesimal parts. This assumption, together with the assumption of independence of degrees of freedom, is what gives us the structure of classical phase space with conjugate variables. The additional assumption of determinism and reversibility the fact that the description of the system at one time is enough to predict its future or reconstruct its past leads us to Hamiltonian mechanics. On the other hand, assuming kinematic equivalence, the idea that trajectories in space are enough to reconstruct the state of the system and vice versa leads to Newtonian mechanics. The combination of all above assumptions instead leads to Lagrangian mechanics, and in particular to massive particles under scalar and vector potential forces.
As a guide to the chapter, here is a list of the main points in the order that they will be presented, one for each section. Review of classical formulations. Lagrangian mechanics is Hamiltonian mechanics and kinematic equivalence. And kinematics in general is not enough to reconstruct dynamics. Hamiltonian mechanics, 1 degree of freedom, is equivalent to determinism and reversibility. Hamiltonian mechanics with multiple degrees of freedom is equivalent to deterministic reversibility and independence of degrees of freedom. And differential calculus and its generalization, differential topology, study infinitely small additive quantities that depend on geometric shapes, i.e. line surface volumes. The principle of least action is a consequence of dr, ind, and ke. I'm not going to keep on saying those.
That's why they are shortened.
Yeah, but I saying the acronym once is kind of worth it. Massive particles under potential forces are a consequence of dr, ind, and ke. Special relativity is a consequence of dr, ind, and ke. Phase space is the only structure that makes distributions state counting, entropy, frame, invariant. Lagrangian mechanics is a consequence of kinematic equivalence. Three-dimensional spaces are the only space for which distributions over directions are frame invariant. And classical particle states as points in phase space are equivalent to IR.
By the way, this is where I believe the latest version and the development versions differ, because for me, I'm seeing point number 11 as Newtonian mechanics as a consequence of KE, right?
Yes. Is it different in? I have the build version, and they look the same to me so far.
I've heard, maybe I misheard that.
Yeah, I also have point 11 as
Lagrangian.
that.
Yeah.
Yeah.
Okay. Maybe I misheard. Okay.
So the only thing that they should be changing in the development version is much later. The classical uncertainty principle is done a lot better. In fact, at that point we're going to switch because the notation and everything else is done much better. But the thing here should hopefully be the same.
Why not switch right now anyways? Might just make things simpler.
Okay. Let me get... So we are going to go in the cutting edge. There we go. So we should be here anyway. So I'll put the link in the chat in case somebody is following for YouTube. There are people following for YouTube, but they're shy. They're not going to introduce themselves. That's fine. Okay.
Okay. Formulations of classical mechanics. In this section, we will briefly review the three main formulations of classical mechanics. Our task is not to present them in detail, but rather to provide a brief summary of the equations so that we can proceed with the comparison. In particular, given that different conventions are used across formulations, within the same formulation and among different contexts, example, relativity, symplectic geometry, we will want to make the notation homogeneous to allow easier comparisons.
Newtonian mechanics. For all formulations, the system is modeled as a collection of point particles, though we will mostly focus on the single particle case. For a Newtonian system, the state of the system at a particular time t is described by the position xi and velocity vi of all its constituents. Each particle has its mass m, not necessarily constant in time, And for each particle, we define kinetic momentum as capital pi I being equal to mvi.
You might want to read the footnote because it has like
Oh yeah, okay. We will use the letter t for the time variable, x for position, and v for velocity, which is a very common notation in Newtonian mechanics. However, we will keep using the same letters in Lagrangian mechanics as well, instead of q and q dot for consistency. Given that the distinction between kinetic and conjugate momentum is an important one, we will denote capital Pi the former and P the latter. The Roman letters I, J, K will be used to span the spatial components. For example, I belongs to 1, 2, 3 for a particle in three-dimensional space, and I belongs to 1, 2 till 3n for n particles, which we will use while we will use the Greek letters alpha, beta, gamma to span space-time components. For example, alpha belongs to 0, 1, 2, 3, where the zero value of the index is used for time. Unlike some texts, xi does not represent Cartesian coordinates, and therefore they should be understood already as generalized coordinates.
Right, so we have equation 1.1, which is Fi as a function of xj, vk, and time equals the partial respective time of capital Pi I. This is just...
It's a total derivative, it's not a partial derivative.
It's not partial, yeah, sorry. I misread. It's total derivative respective time of Pi I. So yeah, this is just Newton's.
Yes.
Mathematically, if the forces Fi are locally...
So you didn't read the sentence before, I guess. The evolution of our system is
sorry.
given by Newton as well. So.
Oh yeah, so yeah, I should go into the evolution for systems given by Newton's second law, which is that, and then now the footnote. For derivatives, we will use the shorthand dt for ddt and delta x, partial x for partial respect to xi. For functions that depend on multiple arguments, we use a free index to know that it depends on all elements. Each argument will have a different index to highlight that there is no relationship between arguments. Okay.
Right, so this is why it's Fi, Xj, Vk in the equation to signify that F spans, so you're going to have n forces, and each force depends on all possible positions, so there is a different index, and every possible velocity, so also the velocity has a different index, while on the right side, the momentum is still an I, so every force is going to be equal to the corresponding moment.
Right.
Or the derivative in time of the corresponding moment.
How come the xj and vk are superscript instead of subscript? Like, how do we determine whether we use that?
So that's a very important thing. So up quantities, you should think them that they depend proportionally with the units of position. So x is going to be always up because it defines the units. The velocity is an up quantity because if you make a change of, let's say you go from meters to kilometers, the velocity is going to change in the same way. It's going to go from meter per second to velocity per second. The force in Newtonian mechanics as written like this is also a contravariant quantity. If you change the units, it will change in that way, and so does the momentum, because the momentum is just a rescaled velocity. There are going to be other quantities that are down, and the quantities that are down means that whenever you make a change in unit, the other quantity changes in the opposite way. This is something that much later in one of the later sections we go through more in detail, but that's essentially how we should think about it.
Okay.
Shall I continue here, or should we?
Yeah, sure, continue.
Okay. Mathematically, the forces Fi are local Lipschitz. Did I read this? Yeah, No, because I went back and
Yeah.
mathematically the forces of higher local Lipschitz continues, then the solution. Well, shall I go to the footnote first?
Yeah.
Lipschitz continuity means that the slope of the function is bounded. For example, square root of x in the neighborhood of 0 is not Lipschitz continuous, as it has a vertical asymptote at that point. One can construct examples, for instance, Norton's dome, where the forces are not locally Lipschitz continuous, and therefore the initial position and velocity do not yield a unique solution. That is, in Norton's dome, the body can stay on the top of the dome indefinitely, or it can fall down after an arbitrary amount of time. In this case, something else outside the system will necessarily determine what it is the motion of the system, and therefore it is not true that the force and the state of the system will determine the dynamics of the system. Okay, going back up. Okay. If the forces are Lipschitz continuous, according to that, then the solution xi of t is unique. That is, given the position and velocity at a given time, we can predict the position and velocity at future times. We'll assume a Newtonian system has this property.
Okay. Other questions about this?
Or we can close the
Yeah, okay.
section on Newtonian before.
An important aspect of Newtonian mechanics is that the equations are not invariant on a coordinate transformation. To distinguish between apparent forces, i.e. those dependent on the choice of frame, and the real ones, we assume the existence of inertial frames. In an inertial frame, there are no apparent forces, and therefore a free system, i.e. no forces, with constant mass, proceeds in a linear uniform motion or stays still. Footnote 4. Recall that linear motion simply means that it describes a line in space, while uniform motion means that the speed is constant. Therefore, we can have linear non-uniform motion, not motion, e.g. an object accelerated along the same direction, or a non-linear uniform motion, e.g. an object going around in a circle at constant speed.
Yeah, this somehow it confuses people. Another thing that I'd like to add is that when you start going to general relativity, this idea of free system inertial frame is exactly what breaks down. Like you do not have the things that are not subjected to forces go in a uniform motion in a straight line, because you have the curvature of space-time, and so things are not going to go straight. So are there any questions on the Newtonian part? If you see Newtonian mechanics, hopefully there shouldn't be any surprise.
I have a question, because I've heard of like some cases where Newtonian mechanics kind of breaks down, or like you don't have a unique solution to a differential equation for like trajectory or something. Does the Lipschitz continuity kind of take care of that? Because I've heard of like Norton's dome is like indeterministic. Is that kind of just fixes
So
those issues?
Lipschitz continue is gonna basically say the solution is unique. That's what you need.
Okay.
And so Norton dome is an example of a potential that is not Lipschitz continuous. And so the way that it works is that you can have this solution that stays at 0 and like stay at the top for an indeterminate amount of time, and then they go down. Like any solution that does that is fine for whatever time. And again, the dome is shaped on purpose such that the potential has that force. Now, realistically, what's going to happen is that the top of the dome is effectively an unstable solution, right? Where if you for a small perturbation, you're going to start and you start falling. And the idea is that it's a limit of such an unstable solution that you literally need no perturbation to make it go. Which of course it's not. It's a physical idealization that actually cannot quite work, right? That's why you have. That's why we're also requiring the forces to be Lipschitz continuous, because we are basically going to assume that that's going to be the realm of Newtonian mechanics. So that becomes a problem with definition. Like, do you consider a Newtonian system where the forces do not give unique solution a Newtonian system? In this setting, we're saying no, the system is not going to be Newtonian. And so just by defining like that, all Newtonian mechanics now is deterministic. And of course, somebody can define things in a different way, and they are happy, that's their right to define the things in the way. The point is that we're defining here things in a specific way such that we can make correspondence to the physical ideas more precise. Right? So we're going to find and carve out what those classes of system that make sense to categorize in a nice way.
Okay, thank you.
We're going to have a similar problem here when we talk about Lagrangian mechanics.
Okay, so Lagrangian mechanics. The state for a Lagrangian system is also given by position xi and velocity vi. The dynamics is specified by a single function, the L dependent on xi, v, j, and t, called the Lagrangian. For each spatial trajectory xi of t, we define the action as the integral of the Lagrangian between t0 and t1. The trajectory taken by the system is the one that makes the action stationary. And yeah, here we see that the variation of the action should be 0. The evolution can equivalently be specified by Euler-Lagrange equations, which say that the partial derivative of the Lagrangian with respect to coordinates is equal to the time derivative of the partial derivative of the Lagrangian with respect to velocities. And that should be it for me.
So bit of a confusion or some question I had here.
Yep.
So you can have this Lagrange wait. Okay. Yeah. So you can have this like you want the variation of the action to be 0. But what if you instead of doing variation of the action, you say you want to minimize the action? Does that give you any particularly special path or?
So the question whether you're maximizing or minimizing the action is basically a matter of convention. Technically what you're asking is for the action to be stationary, which could be either a minimum or a maximum.
Yeah.
Then because of the property that we need to have before to make this unique, it turns out that either they are all minima or they're all maxima. And there is nothing that prevents you to take a Lagrangian and stick a minus sign in front. So at that point, you're going to turn all the minima into maxima and the maxima into minima. So the more correct way is to say the principle of stationary action, but you can always turn the stationary action into a minimal action by choosing a Lagrangian. So it's not that important. The important thing is that the action is stationary. So you just do the variation equals 0. If you wanted to check whether it's minimal or maximal, you should do the second variation and check that the second variation is minimal or like it's you have a concave function or a let's see, no, this is concave and this is convex. I always get them mistaken.
So another thing is like if you have like your standard like what was it or what half m times the what was it p squared over 2m, right? You have like the standard particle Lagrangian. Is that always guaranteed for like the stationary to be minimum?
If you're doing a t minus v type of Lagrangian, yes.
Okay, so that's I guess why they say least action.
Yeah, that's why most of the time, if you're doing field theories, I think that it becomes a little bit more weird. And but it's always better to just say stationary, because when you're writing this equation here, when you do the variation, you're just setting the variation to zero. And so literally you're just asking for the action to be stationary. You're not asking to be a minimum or a maximum.
Is there any actually? Is there any? If there's only if you have the t minus v formulation and there's only a single solution, right? Unique solution, then doesn't that mean that it's the like wait? I'm just wondering if you can like have some sort of convexity property so you can
Yeah,
like
it's in the next paragraph. So let's
okay,
read the
okay.
next paragraph, and then let's go back on that.
Okay. Note that not all Lagrangians lead to a unique solution. For example, L equals 0 will give the same action for all trajectories, and therefore, strictly speaking, all trajectories are possible. The stationary action leads to a unique solution if and only if the Lagrangian is hyperregular, which means that the Hessian matrix is invertible, a Hessian of the Lagrangian. Like in the Newtonian case, we will assume that Lagrangian system satisfies this property. Unlike Newton's second law, both the Lagrangian... I mean, this is a tiny bit, so...
Yeah, okay, go ahead.
Unlike Newton's second law, both the Lagrangian and Euler-Lagrange equations are invariant under coordinate transformations. This means that Lagrangian mechanics is particularly suited to study the symmetries of the system.
Okay, so it's the condition of the Hessian that makes it such that you have a unique solution, and the fact that the Hessian is invertible, it's gonna make that function concave or convex depending on the what's it called, on the determinant of the Hessian.
Okay, yeah.
And that also excludes
There's
saddle points, right?
Say again?
That also excludes saddle points, so you can only have a maximum or a minimum.
Yes, because if there are saddle points, what happens is that you can't, like, you have an eigenstate that is zero
Yes,
for
exactly.
the Hessian. Therefore, the determinant would be zero, and therefore
Yeah,
it's not invertible.
that's what I was thinking. Great.
Yeah.
because if the Hessian is indeed non-invertible, then that actually takes you into constraint dynamics where the phase space is reduced and you're working in a reduced kind of setting anyways, which is, I think I gave a talk about, it's quite interesting, especially if you want to study like gauge symmetries and other kinds of things. Maybe that comes later with phase space formalism.
I actually do not. So the phase space. So the way the phase space is introduced is actually we first introduce the phase space and then we get Lagrangian. So I do not have an intuition if you start from the Lagrangian how the. So what happens is that if you don't have this invertibility, you don't have a bijection with phase space. That's basically what happens. There are some points in which you have to sort of take position and velocity and create some regions, and then only in some of those regions you can go and have a Hamiltonian system. And that part I have absolutely no intuition of how that works actually.
Well, I can actually maybe on Discord maybe share a link of that talk I gave, because I think I'd also look at how the geometry changes when you consider a constrained phase space. You have to,
Okay.
instead of the Poisson bracket, use the Dirac bracket, because
Okay.
once it's non-invertible here, like it's easy to use the inverse function and the theorem essentially to essentially recover the complete phase space. But in the case like here, the pathological case where it's non-invertible, then you come into that. Anyways,
So
tangent.
if you have like physically meaningful examples of Lagrangians that are not hyperregular, but we use in physics to do something, I'd really like to see them. So put them on Discord if you have them.
Okay, yeah, I'll do that. Yeah.
So then on footnote 4, there was a typo. There we can have a linear non-uniform. Oh, notion instead of motion. I would have never seen that. Okay.
I'm fixing it on my
Please.
side, but maybe you can do it on yours. It's quicker.
Yeah, I am fixing it. I have a Text Studio open for exactly this type of thing. It's amazing. There are always typos in everything that you write. There is more than 4 pages. There always will be typos. So, okay, let's continue.
Okay, I think I'm next. Hamiltonian mechanics. In Hamiltonian mechanics, the state of the system is given by position qi and conjugate momentum pi. And so now superscript is like a covariant quantity, and then subscript is contravariant. Is that right?
The other
It's
way
the
around.
opposite.
Okay. Yeah. The dynamics is specified by a single function, h of qi, pj, and t, called the Hamiltonian. We have a footnote. We use a different symbol for position in Hamiltonian mechanics because, well, it is true that qi equals xi. It is also true that the partial of qi is not equal to the partial of xi. The first derivative is taking that constant conjugate momentum, while the second is taking that constant velocity. This creates absolute confusion when mixing and comparing Lagrangian and Hamiltonian concepts, which our notation avoids completely. And then back to the main text. The evolution is given by Hamilton's equations. The absolute time derivative of qi equals the partial derivative with respect to pi of h. Time derivative of pi equals minus the partial with respect to qi of h. Is that the whole paragraph, or should I?
We will again.
We will again want these equations to yield a unique solution, which means the Hamiltonian must be at least differentiable, and the derivatives must at least be Lipschitz continuous. Which I just finished the section there.
Okay, just finish the section and then we can go back to questions.
Hamilton's equations are invariant as well. The Hamiltonian itself is a scalar function, which is often considered mistakenly, as we'll see later, invariant. This formulation is the most suitable for statistical mechanics, as volumes of phase space correctly count the number of possible configurations.
Inequivalence of formulations. It is often stated in
Wait,
physics
are there any
books.
questions first on the Hamiltonian part? Everything's clear? Just to make sure.
So we don't have a if and only if condition for unique solutions. You say it has to be at least differentiable and the derivatives are Lipschitz continuous. Is that like required? Just a necessary condition or just sufficient? In the other two cases, we had like exact.
It should be the same. Like if you have a unique solution, then these things are Lipschitz. Yeah, it should be. I would have to go and reread the theorem. So if it's if it's if and only if in the previous case, it's if and only if in this case as
That
well.
would make sense, right? I expect that.
Yeah.
So
Because these are just this is just like Newtonian mechanics, right? These are total derivatives, and they are equal to a function, and then the function has to be Lipschitz continuous to be able to guarantee unique solution. Now,
yes.
I don't remember if the theorem is an if and only if. I think it is, but with all these mathematical details, I always am a little bit.
I mean, the equations, like mathematically, this is structurally like almost the same, right? You just have okay, that will make sense.
It's just that in Newtonian mechanics you would have a force directly, and here you have the derivative of the Hamiltonian. So it's the derivative of the Hamiltonian that has to be Lipschitz continuous.
Yeah. Okay.
I think it is an if and only if because it's a second order ODE with you specify the velocity.
Right.
So yeah, you have uniqueness in existence.
Very good. Thank you for the confirmation.
Okay, I'll continue the
Yep.
inequivalence of formulations. It is often
Oh,
stated in physics
actually,
books.
wait a second, because it's already 10:50. This section is going to be quite long. So I'm trying to understand where do we want to stop? So we can probably, up to here, I think it's still gonna be fine. Like I'm worrying about starting some things that then we have to remember for next time. So, okay, please go ahead.
Okay.
Inequivalence of
Inequivalence of formulations. It is often stated in physics books that all three formulations of classical mechanics are equivalent. We will look at this claim in detail and conclude that this is not the case. There are systems that can be described by one formulation and not any another. More precisely, the set of Lagrangian systems is exactly the intersection of Newtonian and Hamiltonian systems.
Okay, testing equivalence. We will consider two formalisms equivalent if they can be applied to exactly the same systems. That is, Newtonian and Lagrangian mechanics are equivalent if any system that can be described using Newtonian mechanics can also be described by Lagrangian mechanics and vice versa. In general, in physics, great emphasis is put on systems that can indeed be studied by all three, leaving the impression this is always doable. Footnote 6, let's see. If one asks the average physicist whether Newtonian and Hamiltonian mechanics are equivalent, the answer most of the time will be enthusiastically positive. If one then asks for the Hamiltonian for a damped harmonic oscillator, the typical reaction is annoyance due to the nonsensical question. Damped harmonic oscillators do not conserve energy, followed by a realization and partial retraction of the previous claim. The moral of the story is to never take these claims at face value. Going back to the text. Okay, leaving the impression this is always doable. However, just with a cursory glance, we realize that this can't possibly be the case.
It's my turn. The dynamics of a Newtonian system, in fact, is specified by three independently chosen functions of position and velocity. The forces applied to each degree of freedom, DOF. On the other hand, the dynamics of Lagrangian and Hamiltonian systems is specified by a single function of position and velocity slash momentum, the Lagrangian slash Hamiltonian. Intuitively, there are more choices in the dynamics of Newtonian systems than for Lagrangian and Hamiltonian.
Now, the reality is a bit trickier because the mathematical expression of the forces is not enough to fully characterize the physical system. We need to know in which frame we are, what coordinates are being used, and the mass of the system, which is potentially a function of time. On the Lagrangian side, note that the Euler-Lagrange equations are homogeneous in the Lagrangian. This means that multiplying the Lagrangian by a constant leads to the same solutions, meaning that the same system can be described by more than one Lagrangian. The converse is also true. If one system is half as massive and is subjected to a force half as intense, the resulting Lagrangian is also simply rescaled by a constant factor. Therefore, the map between Lagrangians and Lagrangian systems is not one-to-one, it is many-to-many. This is why we should never look simply at mathematical structures if we want to fully understand the physics they describe.
Regardless, our task is at the moment much simpler. We only need to show that there are Newtonian systems not expressible by Lagrangian or Hamiltonian mechanics. We can therefore limit ourselves to systems with a specific constant mass m in an inertial frame and write the acceleration is equal to the force divided by the mass. Given that the force is arbitrary, the acceleration can be an arbitrary function of position, velocity, and time. Similarly, we can write the acceleration of a Lagrangian system as the acceleration is equal to the force as a function of L divided by the mass. That is, the acceleration is going to be some function of the, okay, I just said that. Given the Euler-Lagrange equations 1.3, the map between the Lagrangian and the acceleration must be continuous in both directions. That's a typo, it should be plural.
Where is the typo?
Acceleration must be continuous in both direction.
Ah, jeez. The S's are my worst enemies. I always put them or leave them out, and then I can never see them. Okay. Yeah, go ahead. I'll fix them.
For small variation of the Lagrangian, we must have a small variation of the equations of motion and therefore of the acceleration. And for small variations of the equations of motions, that's inconsistent there. One of the equations of motion should probably be
Should it also
Oh.
be for small variations of the Lagrangian, like right after the colon?
yeah, do we have multiple equations of motions or one equation of motions?
We have multiple equation of one motion. There's no equation of motions.
Okay,
So
well
that's
then,
for sure. Okay, so for small variations, right?
for
For
a
small
small, yeah,
variation.
that needs to be a small variation. Okay.
Okay, so for small variations of a Lagrangian, we must have a small variation.
Or maybe for a small variation of Lagrangian.
Yes, yes. So let's make them for a small variation of the Lagrangian, we must have a small variation of the equations of motion, and therefore the acceleration for small variations of the equation of motion, we must have a small, for a small variation of the equations of motion, we must have a small variation of the Lagrange. There you go.
But a continuous surjective map from the space of a small single function, i.e. the Lagrangian, to space of multiple functions, i.e. those which specify the acceleration in terms of position and velocity, does not exist. This is because mathematically the space of continuous functions CRR and CRN to R are not homeomorphic. Intuitively, the underlying reason is the same as to why a map from a volume to a line can't be continuous. In a volume, you have infinitely many directions you can move away from a point, but while on a line, you only have two. Also, I should point out that map from a line to a volume can be continuous. That's the Hilbert curve, I think.
They can't be by homomorphism.
Yeah, but you can do one way, but not the other, really. Anyways.
Yeah. Isn't that what I'm saying?
Yeah. Well, you don't particularly bring up the counter, the opposite. Anyways. And
Okay.
therefore, there must be at least one Newtonian system with constant mass expressed in inertial framed as not describable using Lagrangian mechanics. The same argument also applies for Hamiltonian mechanics, since the dynamics in this case are also described by a single function in the same number of arguments. We therefore reach the following conclusion. Not all Newtonian systems are Lagrangian and or Hamiltonian. And yeah, here's another typo. The dynamics in this case is also described to be R.
Where is it?
The same argument applies for Hamiltonian mechanics, since the dynamics in this case is also described. That should be R, I think.
Is the dynamic is? I thought dynamics is singular.
Dynamics is plural, right? Dynamics in this case are also described.
There I'll have to ask Christine because I thought that was singular. She made me have it singular. Dynamics. The dynamics. Anyway, I'll take it
maybe
offline
look it
and
up
check.
later. I'm not quite certain, but
Yeah.
Isn't it like the same as mechanics is singular and like kinematics is singular? Same with
Right,
dynamics.
exactly.
Yeah, that's what I thought too. Again, I could be wrong. Should check.
Yeah. The mechanics is the kinematics is the dynamics is.
I guess, yeah. It looks plural though, but yeah. English is
I'm not a native English speaker, so you know.
I mean, I can tell you in Ukrainian it's singular, but it doesn't help. I mean,
Oh, Andrea Cortes from the chat says, "I'm sure dynamics is singular." So
Right, okay, here we go.
We have another independent confirmation. Okay, so it's the hour, so I would stop here. Even though I would like, I'm not so tired that I wouldn't continue, but I think it's also harder for people, online to follow this. So I think we should keep them an hour. But I'm welcome to open to question if people have question and want to discuss other things. I am here. Otherwise, we can close it and leave it for next week. In particular, if anybody has a comment or suggestion of if this went well or not, how to improve, I'm of course they would have the priority.
I have more of an organizational question for next week.
Yes.
Would everyone be fine moving it an hour later for that 1 week? I have like a meeting at my job that I cannot reschedule, so that would be very helpful. If not, I'll read myself and rejoin you a week later.
For me, it's fine.
I think it
Yeah.
should be fine because we
Good.
had like a 2-hour block
Yeah.
when we did the calendar.
Good with me.
Great, thank you.
Yeah, I think this went well. I was kind of skeptical at first, like just reading it paragraph by paragraph. I was thinking maybe like we would read in advance. But I think with, people are starting school now and stuff, and it's a little busier. I think this is very palatable for a weekly meeting.
Yeah, so the reason, so that way there is no, so what would happen if we say, oh, people have to read, is that a lot of the time people are not going to read, and then they fall behind, and then they drop, and then we don't have a reading group because the number diminishes, right? If it's just, you just have to show up, then it's a much lower bar, and given that, some people are working and so on. If there are other people who are interested in joining sort of online, send me an email and I will add you to the Discord server, and then you can get all the notifications for everything. Yeah. So have we decided to move to 11 for next week then? Everybody agrees?
Yeah.
Sure.
Okay, so I will have to remember to change things. Any other questions from the chat or from the group? I'll give it another 10 seconds because there is a delay for the chat when I talk and when. Okay, so I don't think there are questions. So thank you very much for everybody for joining. So I hope this was useful, and I'm gonna see everybody next week.
Yeah, see you next
Everyone.
week. Thank you,
Bye
everyone.
bye. Have a nice
Yeah,
week.
thank you.
Bye. And now I have to find the button to end the stream. There we go.